All right, greetings everyone. This is Doc Eason and welcome to another video. We of course have to do another science application. That's what we're going to be doing today. And actually this video is actually a video series that's comprised of two videos, because what we're going to do is we're going to break it up into two steps. And so each video is devoted to each one of those steps respectively. Now, what are we going to be doing? So in this video, what we're going to do is we're going to formulate a way to measure the temperature of what's known as the cosmic background radiation, which is something that it's a form of faint or light radiation, which is believed to permeate all of space. You can't go anywhere and actually not see the evidence of its presence. So this is something that we're going to formulate. We're going to work out, some equations and the method that we're going to solve those equations. And then we're going to work all that out and put it into Python code. And then we're going to use data that's given to us by NASA from one of their satellites, which has measured spectrum data from the cosmic background radiation. So we're going to take their data, and then we're going to run our program on their data to actually extract the temperature and see if we can get the same information, the same answer that NASA has obtained with their data. All right, so that's what we're going to be doing in these two parts for this series. And I hope you are ready to rock and roll, because that's what it's going down. Now, this series is actually taken from, as a small part, has been cut out, I should say, of a larger course called From Thermodynamics to Quantum Physics, which teaches people about, more in depth about thermodynamics and its connection to quantum physics. All right, so we're going to be talking about basically Planck's distribution and a lot of things around related to that. And so we're going to be applying all of those things in this tutorial, if you will. All right, but if you're interested in a course that goes deeper into the stuff you're going to see in this video series, then check out the link in the description below, as well as the link to the code, the source code, which you'll find on GitHub. All right, so without any more rambling, let's get started. All right, we'll see you on the other end. Peace. All right, so welcome to this virtual lab using Python. In this lab, what we're going to do is we're going to make use of Planck's blackbody distribution formula, which we've been working out and discussing in this particular course or module. And what we're going to do in particular is we're going to start with or take data that's been published by NASA from one of their satellites, which is known as a COBE or COBE satellite. And that satellite has measurement data, essentially a spectrum data. And what we're going to do is take that data, we're going to extract it from information that they share with the public, and we're going to take it into Python, and we're going to automate the measurement of the temperature from that data. So we're going to see if we can reproduce the temperature that NASA has also basically figured out using their own methods. And so we're going to do that in kind of two steps. First, we're going to discuss what the formulation is, which is how we're going to tackle this, such that what I really want to do, all I want is someone to pass me data, and I really I want it to any kind of spectrum data, but I'm going to do it in such a way that I don't really care what the units of the data are, as long as it's a frequency dependent data. But I want it to be, the formulation be insensitive to whatever the units that they choose. And I'll say a little bit about that in just a moment. So we're going to formulate something along those lines, and then we're going to jump into Python and we're going to code it up, and then we're going to execute the code, and then we're going to predict the temperature of the cosmic background radiation. All right, so let's get going. All right, so if you look at the left is a figure, and I know that there's a lot on this slide. We're going to kind of walk through this slowly, but if you look on the left, there is a graph or a plot of some data points, and you'll see here written COBE satellite data. So I've actually taken this figure directly from Wikipedia page on cosmic background radiation, or you can also get it, I believe, from the COBE's Wikipedia page. And so this satellite has actually basically measured data and that's represented by these red crosshairs on this graph. All right, so each of these little discrete points is the actual measurement data, and the blue line that you see here is data that NASA has fit, okay, using a blackbody spectrum. And by doing that, one can extract the temperature. So what we want to do is actually see if we can verify or reproduce what NASA has basically calculated. And we want to make sure that that process is automated such that we don't really care what data that we're looking at. As long as we know it's a black body spectrum, we will be able to basically extract the temperature out of that data. All right, so that's the goal for us. So if you notice here on the first x-axis, there are units here, which is they denote their units in 1/centimeters or inverse centimeters, which is proportional to frequency. And then we also have on the y-axis also units. And these units, we're gonna formulate this problem in such a way that I don't really care what units they use, particularly on this axis. All right, because someone might choose different units over here. Of course, there needs to be in terms of frequency for the x-axis, but for the y-axis, I really don't want to have to worry about what kind of units they use. And the way that I can do that is by dividing this curve, or normalizing this curve, as we say often, is taking this curve and dividing it by its peak value or its maximum value, which is this value right here. So if I were to divide this entire curve or set of data points by the peak value, well, then we'll have a curve whose peak value is 1. And this will be true for any measurement data that we're given. The trick is we have to actually formulate the equations and things that we're going to be working with to be consistent with that formulation. And it is indeed a little bit more work to it, but it's worth it because we then have a method that is insensitive to the units that are going to be used when the measurement data comes our way. All right. So we got these in total, there are n data points that are measured along frequency axis. And we have the ith data point. And what we want to do is we're going to define, if you look down here to the lower left, we're defining what we're calling a cost function, which is what we want to minimize. And this cost function is going to actually be the sum over all of these data points. And so, as I mentioned, there's the ith data point, so there's n total data points across the frequency axis. What we're going to do is sum all of what I label here as epsilon, but these are just differences or errors between the normalized Planck's function and the data point of the measurement. So if this was one of the points, then that would be one of the values of this little d here, little d sub I. That'd be the ith point. So that would be this the value for little d sub I. And then we would also use a normalized version of Planck's distribution, and that will be basically the value that we use here. So this is an analytical function, which we know all the information about this function. So we would have this function that would be evaluated at that particular frequency. So every point on here is basically a value from the spectrum corresponding to a particular frequency. So we'll plug that frequency into our Planck's function, and then we'll also use the data point corresponding to that frequency, and we'll calculate the difference between those, and we square that. And what we want to do is minimize this function. And so this is really the objective that we are after here. So how can we do that? Because the reason why we can use something like this is because this, after all this summation and across all the data points, at the end of the day, we have just some function of temperature, because we want to know what the temperature is for this curve, and that's basically involved or included in Planck's function. So when we calculate this cost function, at the end of the day, it's going to be some function of temperature. All right. So again, because we want to be insensitive to this, whatever data points whatever scale or units are used for the measurement. So to do that, we're going to just divide by this peak value, and we can do that analytically with Planck's distribution as well. And we'll talk about that in just a moment. So when you see this P star, which is in the cost function, P star represents Planck's distribution but being normalized, just like we did with the data. We're going to normalize this function by its peak value, and that's what we mean by P star. So it's not exactly the same as P. It's P divided by that peak value, and that's what P star is. All of it, even once you divide by P star, is still a function of temperature. All right, so and then this DI is that ith measurement point, which we discussed that earlier. So these are each of these corresponding measurement points or data points, and those are what the D sub I, which is basically used in our cost function. So we're summing all of these little things up, squaring those, and what we want to do is now minimize this function in such a way that we can find by, finding the temperature that fits this curve to this data. All right, and that's the way that we minimize our cost function. All right, so that's what we're going to do, and we're going to basically utilize or take advantage of the fact that we know Planck's distribution exactly what it is. It's this function here. Looks a little crazy, but all of these things like h is a constant, c is the speed of light, that's a constant, and h, I forgot to mention, is Planck's constant, and then f is the frequency, which is of course one of the data points that, or one of the parameters of the data that we're going to be throwing into this function. And then we see that we have this temperature involved in this equation. So we're going to be using all of this to basically extract the temperature from the data. All right, so hopefully this makes sense, but we'll continue kind of fine-tuning this conversation in the formulation. So let's keep going. So what do we do with this cost function that we just talked about, which is we're summing over the data points, all of the data points. We're going to sum over all of them, and there's total of n of those, and each data point is the ith data point. And so we're summing over those, this epsilon, which epsilon here is just shorthand for the normalized Planck's function evaluated at that particular frequency of the data point, which is also a function of temperature, minus the actual data point, which is given here. And that data point needs to be also normalized. All right, so divided by its peak value. So we have this function that we want to minimize. And in order to do that, all we got to do is take our cost function, take the derivative of this with respect to take the derivative of the cost function with respect to the variable that we're talking about, which is temperature. Now, so we're going to take the derivative of that cost function with respect to temperature and set that equal to 0. And this is the way we're going to find this out. So what I want to kind of point out, I'm not going to go into detail on this, but why am I able to write this equation right here? It's not the value right here, because this curve is a function of frequency. And so that's actually, that value there is the derivative of this function as a function of frequency. And so that is 0, yes, but this is not the same thing. This is the derivative of our cost function. We're saying that that is equal to 0. And this is actually coming to us from basically maybe a less obvious result, which was discussed actually in the very first module, where we talked about something known as the Euler's formula. The Euler equation is a differential equation that allows us to take any kind of function, like a cost function, and in that module we call it the action. And we can basically use a specific formula, and based on basically if the function is if it depends on some value, in this case it's temperature, and if it depends on temperature as well as the derivatives of temperature, then we have a prescription for how we can actually work out an equation based on that. And it ends up simplifying to this for our case, because this cost function is only a function of temperature, but yet it's not a function of any of its derivatives. And so that's kind of just a little bit of background on where this comes from. It's not coming from taking the derivative of this function because we see that little hump there and the slope there is 0, but that's not what this is. All right, but we still have the derivative of our cost function must vanish, and that comes from a more subtle kind of formulation, which is known as Euler's equation. All right, but don't worry so much about that. We're going to use the result here, which is, again, the derivative with respect to temperature is equal to 0. All right, and again, we're reminding ourselves that this P is Planck's function divided by its peak value, and then we're summing that up over all of our data points. All right, so hopefully this makes sense, and by doing that, we are able to basically fit any data. It doesn't really matter what it is, as long as it's valid data and it's a spectrum data, we can extract this. We'll be able to extract the temperature from it by this formulation. All right, so let's keep going. So how are we going to do that exactly? So we just got to the point where we see an equation that we can basically come up with that takes that cost function, that sum, and we take a derivative of that with respect to temperature, and let's call that function f of t, because it's also a function of temperature. Since c is a function of temperature, then so is its derivative. So we have some function of temperature, and that function, whatever it ends up being, is equal to 0. This is coming from the result we just said, where dc dt is equal to 0. But whatever this function ends up being, let's just call it f, and that function is equal to 0. Well, we know that any function that we can write that equals to 0 is a special type of equation where we can find values of t that make this non-zero function equal 0, and therefore these values of t are known as roots, R-O-O-T-S, roots. And so we can use methods that allow us to find the roots of an equation to actually find out where the temperature is that satisfies this equation. And that's exactly what we're going to do. So we're going to basically use a method called Newton's method. And that method is a well-known method, but allows a person to basically iteratively find the roots of a nonlinear equation which equals to 0, or any equation. But if it's a nonlinear equation and that equation is set equal to 0, we can use a method like this to actually iteratively find the values of that variable. In this case, it's the temperature, where that function is equal to 0. All right, so that's that's the power of Newton's method, and this is the formula for it, where this T sub I plus 1 is the I plus 1 temperature, and we get this value by calculating something based on the previous value of the temperature, which is the ith value. And so that's T sub I minus this ratio of the two functions. So this is the function, this function up here, which is f of t. So we have that function, and this function divided by its derivative. And that's what this f prime is denoting, the derivative with respect to temperature. So t minus f of t divided by f prime of t. This is Newton's formula, and this f prime of t is the derivative of this function. So that means the second derivative of the cost function, which is the first derivative of f. All right, so I know so we got to kind of keep all the pieces organized so we can make sure we get it right. But we have a function we call f. It happens to be the derivative of the cost function, but we also need the derivative of f in order to use Newton's method, which means that we need c, we need its derivative, and we also need its second derivative. All right, so this is what we need, and we can do all of this because we have a function which is analytic. It's exactly analytic when it involves the Planck's distribution, which we have this formula or this function readily available. All right, so we can do all of these things. So this is what we're going to do, is we're going to be utilizing this iterative method using the function that we just defined, which is the derivative of the cost function, and we'll get its derivative, and then we'll put all these pieces together, and then we'll figure out exactly what the temperature is based on the Newton's iterative method. All right, so let's keep going. So let's talk a little bit about this normalization of the function, because this does complicate things a little bit more than if we didn't do that. But like I said, the reason we want to do this is because we want to create a method that leaves us insensitive to the units that are used in the measurement. If someone wants to use SI units or any other type of unit, we want to be insensitive to that. And the way we do that, our little workaround, is to normalize the function by its peak value. And we can do that readily with Planck's distribution because we know what its peak value is. And so that's, how we can do that. So here we have, just summarizing or repeating what we said earlier in the earlier slides. We have the cost function, then we have the derivative of the cost function with respect to temperature, and that we're calling f, and all of that, which becomes 2 times this, because this is squared. So when you differentiate, you get a 2 in front, times this difference, which is the normalized Planck's function minus our data point. It's part of this sum, and all of that multiplies now by so when you take this derivative, it's 2 times this times the derivative of this, which is a temperature dependent function. So that's where this comes from. So this is the function that we basically need to treat as our f of t, which we want to find the root. We want to find the temperature that makes this sum equal to 0, and that is going to be synonymous with the temperature that is the fit of this, of data point, which gives us the actual temperature of the black body. That's the idea. So we have our function here, And we now just are looking at taking this P of t, which is just Planck's distribution, and we're now seeing that this P star, which we've written up here, is actually just the same thing, but we're now dividing it by the maximum value, which corresponds to these guys. For any of these distributions, we need to pluck off these maximum values, and we divide by that so that the curve peaks out at 1 for any value, for any curve or data that we have. So this is the function that we have to work with. Instead of P of t, we're working with P of t divided by this peak value. And that peak value, we're going to discuss it in just a second, is actually a function of temperature. So let's see exactly how that is. So we're going to use, in order to get this peak value, we're going to use a result which is also well known, and we talked about this and we derived this result also in this class earlier. Hopefully you remember that. And that result is Wien's displacement law. And it's a law that says for these distributions, we know that the location where the maximum wavelength occurs, remember this is wavelength, not frequency. We're going to relate the two, but basically the location where the maximum occurs, the frequency or the wavelength, excuse me, multiplied by its temperature, multiplied by temperature is equal to a constant. We know this from Wien's displacement law, and we derived this exactly or explicitly in our other lab, where we took this formula and we basically found these points that equal to 0, and this allows us to actually get, because the condition here is that the derivative is equal to 0, so we worked all that out and we found that we can get this relationship. All right, so this is in SI units. So the value or the location of the maximum wavelength, or the wavelength where the maximum occurs, that's what we mean here by lambda sub max, is inversely proportional to the temperature. It's just a constant, just some number divided by T, which is its temperature. All right, so we can use the relationship between wavelength and frequency. So that wavelength, and this is specific to photons, we can take the wavelength of a photon multiplied by the frequency of the photon, and we know that gives us the speed of light. All right, the speed of the photon. So that means if we know this lambda max, then we can basically, from this, figure out what the corresponding frequency max is. So the corresponding frequency is just going to be c divided by this lambda max. So we get this function, which is proportional to temperature. This little c here is just the speed of light, something like 3 times 10 to the 8 meters per second. And then we also have just, so this is just a constant multiplied by temperature. And this is the value for the maximum frequency, or where on the curve this frequency occurs. And we know that this is true for these blackbody radiation spectrums. All right. So we're going to take this result, the maximum frequency, or the location where the peak is, call it f sub max, and we're going to substitute this expression, which is a function of temperature, so it's just proportional to temperature. We're going to substitute this into Planck's equation, which is a function of frequency. So if we plug this f max into this equation, we're just going to get another function of temperature, because this is a function of temperature, and we're going to substitute this into this equation. So we're just going to get another function of temperature, which is P max. This is the P max, which is not just a function of temperature. And that function we can evaluate based on, whatever, basically it's only a function of temperature in this case. So we can evaluate it, or we can use it in our iterative process, in an iterative method, evaluating temperatures in the same way we will with this function. All right, so we just have to pass it. We'll pass the temperature to both P as well as P max, so we can calculate P over P max, which is the normalized Planck's function. All right, so this is what we're going to do. So we're going to basically tie Wien's displacement law, which tells us the relationship between where these maximums occur, those frequencies and or wavelengths, and that allows us to actually put together the function of temperature, which gives us that peak value for this function, and then we're going to use that to normalize Planck's function. All right, so that's what we're going to be doing. So let's kind of put all this stuff together. So it's quite a bit, I know, but this is everything. We want to talk about this because, like I said, it's not a very straightforward or simple process, but it is. Well, actually, it is straightforward, but it needs some discussion so that you kind of understand what's going on. So when we implement this, you'll know why we're doing what we're doing. All right. So we're starting out with Planck's distribution, and that's over here on the top left. P of t, that's just Planck's formula. And we know that, we have this cost function, and we found out that differentiating the cost function and setting that equal to 0 gives us our function f of t. And we find out that that is given by this. It's our sum over our data points, over our n data points, and we're summing up 2 times this difference here, multiplied by the derivative, the derivative of p star, which is the normalized function. And all of that gets set equal to 0. And then we need the derivative of that, which is f prime, which we've worked out, and that is basically given by this expression. It's a little bit lengthy, but this is basically the result of taking the derivative of f prime. And I might have skipped. No, I didn't. All right. So this is the value, this is the formulation, so to speak, that we can use in order to, in the Newton's method, where we have temperatures that we're going to basically start with some initial value of temperature, and we're going to iterate through using Newton's method. And Newton's method requires that we have this function f, which we've defined over here, and f prime, which is just its derivative, in this case, with respect to temperature. And we're going to actually put these two together in Newton's method and iterate so that we can basically converge to a solution and find the temperature that matches our Planck's function being normalized to our data. All right, so that's what we're doing. And just, so the P max is just Planck's function evaluated at that F max, where this F max is just some constant. This little c here is speed of light, divided by this number here. And then, so now we have P star, which is just Planck's function divided by this. All right. So this is what we're putting together now. So we just got to code all this up. So yes, it's quite a bit, but we're going to just do it step by step. So first, for example, we can code out Planck's function. And then we'll code out the peak value of the function and all the little pieces that we need to calculate the peak of the function. And then we can basically calculate the derivatives in a pretty straightforward way, utilizing all of those things together. And then we'll piece this together so that all we'll have to do in the end is call these functions, and we'll iterate and get our result. All right, so that's what we're going to do. All right, so just a word about these derivatives, just in case you want to see how do you get those derivatives. And so since we know this P star, which is this normalized Planck's function, it's the Planck's function divided by that peak value. That's what we defined it to be. And so if we take the derivative of this, the first derivative, then what we need to do is basically recognize that both of these are functions of temperature. So we can kind of do, the derivative is going to actually be 2 parts. You can either do it more than one way, but we're going to treat this like the product rule. So I'm going to basically treat this like P times 1 divided by P max. So P times 1 over P max, and just do a product rule. So the first time I'll get, or the first part, is going to be 1 over P max times the derivative of P. So just this being constant, taking the derivative of the top. And that's what we get, 1 over P max times dP dt. So the derivative of Planck's function with respect to temperature. And then what we're going to do is then add the second part, which is P times the derivative of 1 over P max. And that's what this second part is. And that is, since 1 over P max is also P to the minus 1. So you take the derivative of that, you get a minus sign, and that's where this comes from. You get a minus sign, and then you have to subtract another in the power. So it becomes minus P squared. So that's what this, minus 1 over P squared. And so that's what this becomes. And then we still have our P, so that's still in the numerator. So we have this minus 1 over P squared times the derivative of P max with respect to temperature. And that's what this term is. And that gives us the first derivative. And then now remember that in Newton's method, if we go back, we know Newton's method, we use F and F prime, and F prime needs both the derivative, the first derivative of P star, and also the second derivative. So there's some work involved here. So we got to calculate the second derivative as well, and I'm not going to step through it, but I'm just going to put the result here so you can see it, and that's a typo. I put 2 minus signs. It should be just 1. But this is the result when you calculate the derivative of this, which is the second derivative of P star with respect to temperature. So this formula, this result down here, is what is the last part to the formulation, which gives us, so now we have first derivative of P star, and we have the second derivative of P star. So, woo! All right, so a little bit of work there, right? I know. But like I said, it's worth it, because once we put all these pieces together, we'll be able to actually fit any data, regardless of the units, as far as the y-axis, regardless of the units. And all we have to do is basically throw their data at our, basically plug their data into this program, and it'll fit it and extract the temperature without being sensitive to that kind of detail. Okay, so that's why we want to do it this way. All right, so let's go ahead and kind of round this out, and go ahead, and now we can, I guess, transition into the coding part. But hopefully this makes sense. I know there's a lot going on here where we want to kind of piece it all together. So we need to discuss this formulation so we can understand how we go about solving a problem like this, and how can we, get things like the temperature from a black body using Planck's distribution. And this is a way that we can do it. In particular here, we're setting up a problem where we're starting with measurement data. So that's discrete data. And we're going to formulate things in such a way that we can take this discrete data, and then we can actually extract the temperature from that. So that's what we're doing. All right, so now let's go ahead and transition and do it in Python. All right, so let's do that now. All right, see you in just a second. Okay, and just to make a correction there, of course, I mentioned earlier in the video that the Python coding part is in the second video of the series. So this is where we'll end the video, and please check out the second part if you want to hang out and do the Python coding with us, and we'll see you on the other side. All right, peace.